The genesis of this project partly occurred in the period of 2008-2009. I was one of the U.S. Attendees at the Conference of Parties in Copenhagen, and had a chance to talk to many of the policy people there. One thing that struck me was that there was a universal perception that wind and solar energy would probably only play a small part in future energy because it was too variable. It was too low density, couldn't really fit into the grid system. And I subsequently looked at much of the literature on it, and the thing that really surprised me was how they treated weather in these studies. I've spent my whole life studying weather, and I felt like weather, contrary to a lot of people's understanding, actually varies on very large scales, which means if the key to things like wind and solar energy are that if it's not blowing in part of the domain, it needs to be available in other parts of the domain, it means that you have to get to big domains. So I started off with a study that I thought I could do in 3 months, and just me and a junior scientist. It's taken 5 years, and I think we have some pretty exciting results, and I look forward to presenting them. As Paul mentioned, Chris Clack is our chief person. I realize nobody can see this red, but we have 4 other authors of our work: Annalise Alexander, Adam Dunbar, Yuan Fouché, and James Wilczak. And essentially, the thesis of our work is that geographic scale dictates the carbon mitigation and cost reduction potential of wind and solar systems. And these are sort of heterogeneous systems that include wind, solar, and we're going to talk about gas. This is a picture of where Chris and I work. It's at the foot of the Rockies near NCAR in Boulder. Some of you know that. This is the NOAA research building. And our laboratory that I'm director of has 550 people. We do weather, climate, and atmospheric chemistry, which is a huge positive. If you're the director and you need some help on weather data, you generally get it. So even though we had a small group, we got a lot of help. And I'd like to start with some work that was done by our laboratory from 3 people from our laboratory. One of them is Dr. David Hoffman, who is the late Dr. David Hoffman. He ran our global network, so Mauna Loa carbon observations all around the world that we run from our laboratory. It's a pretty famous network. What David did was he took the post-industrial CO2 and subtracted off 278, which was the pre-industrial value, and put it on a logarithmic diagram here on the ordinate. So this is parts per million of CO2 above the pre-industrial. And we all know that a logarithmic, a line of an exponential is a straight line if you put it on a logarithm. And so what we see is that there's a very deep and simple relationship that as time goes on, this is almost perfectly linear. So what that really says is that there's some function of the exponent that's constant, and it's 2 things. One of them is population growth, and the other one is per capita CO2 emissions in the population. And the neat thing about this paper by David Hoffman was that he basically put them together, e to the a plus b. And so what you see, for example, in China, as population growth went down, per capita CO2 emissions go up. And that's why you get this almost perfect straight line. which I think David's argument that it's just going to keep right going right up to here, the doubling of CO2 in 2050. This is a value that doesn't end right here. I'd like to comment now on another paper. Dr. Susan Solomon was another person. She led Working Group 3 of the AR4 of IPCC. She's also in our lab. There was a paper in Nature Geoscience that basically said, what was CO2 in the past? So you can relate the amount of CO2 in the paleo history that we're really right now the equivalent of Pliocene CO2. And I have this statement over here, the equilibrium climate. So we don't immediately go to the Pliocene. You've got this big complicated Earth system that's going to try to get there in its own way, and parts of it are going to take place fast. I published a paper in the National Academy in the US on that in 2001. So essentially, we're on a fast track to the Eocene. The Eocene was an ice-free Earth. So if we look at kind of where we are now, if we stay on this curve to 2050, and even if we reverse it, at that time, we're going to overshoot on concentration to above 700 parts per million and stay above 500 for a couple years. So we have to reduce CO2 well before 2050 if we're going to stop this overshoot into the Eocene era in terms of equilibrium climate. So now I want to switch to weather. And again, people who say, well, wind and solar are too variable, they tend to think of the way power is now handled in the US and Europe and elsewhere, and that is with AC power you tend to optimize over small domains. But if you look at weather, this is a big high in eastern United States, there's a big low in the West Coast, and we know from studies of atmospheric kinetic energy that the real scale of weather is a couple thousand kilometers. In fact, the reason it's that large, the Rossby radius of deformation for large waves, is that the energy comes in barotropic and baroclinic instability in these very large scales, and it only cascades down. It doesn't create energy at higher resolution. So here's a chart that kind of shows that. So we have here the planetary scales where atmospheric energy is generated. When I say baroclinic, I mean a big old storm that covers several thousand kilometers across. And if you look at the size of the US 48 states or the European Union or so on, it actually gets almost up to that energy scale. Whereas if you look at the size of a European country, a US state, or where we actually sort of balance our power, it's way down here. This is called the entropy cascade. My first refereed paper sort of explained, was actually probably nothing too original, but it kind of explains the reasons why you get almost 3 orders magnitude more energy in the large scale as you do down here at small scales. And what does this really mean? What it means is, if you're going to design your energy system so that if the wind is not blowing here, but it's always blowing somewhere else in the domain where you can exchange power, then you want to get to these big scales. That's a simple statement of what the weather is. You want to have a domain big enough so if it's not blowing here, if the sun's not shining here, it's shining somewhere else. So we set out to study the energy system. And to do it, we used a model developed in my laboratory called the Rapid Update Cycle Model. It takes a very rich data area, the United States, 48 states. It uses 3D variational analysis. It takes literally 20 to 30,000 observations every hour and converts them into a full grid in the vertical that allows us to get the vertical winds. It has cloud, and we use the satellite to get the sun right. So the big thing we put our efforts into was an hourly database for 3 years, 2007, 8, and 9, with the wind and solar measures extremely accurate. Huge amount of work to make that right, starting with this weather assimilation model. And I want to get to the second sort of big factor in thinking about wind and solar energy. And that factor is some places are really rich in resources, and some places are really poor in resources. That's just about like any other economic thing that you can think of. Do you want to dig a gold mine in your backyard? Good luck, because there isn't going to be much gold there. But somehow people had it in their heads, well, you know, we'll just let every little area sort of generate their own wind and solar energy, and that'll be good. And if you look at some of those, they end up with wind and solar energy costs about 5 times as much as our current costs. So that doesn't work. And what you see here is what I call over the US the wind triangle. There's something equivalent over Europe and over China, and I'm going to show you some of those results. But this is the US wind triangle, which is an area where essentially if you set up your wind turbine, you're going to be able to buy power for about 5 cents a kilowatt hour, or in pence, 3.5 pence per kilowatt hour. So this is an area where there's really cheap wind. And if you had some way to move that to markets where there isn't cheap wind, and this is an annual wind capacity factor average, wind capacity factor being the percent of wind energy that you would get by having something there the whole year. So 50% means if you had a 1 megawatt turbine, you get on the average about 500 kilowatts averaged over the whole year. So a big part of why it makes sense to look, you know, at least think about larger domains, and of course it isn't good enough to think about it, you got to make it quantitative, and you're going to see that. It is that it's really cheap in some places, it's expensive in other places, and you want to get access to the cheaper sources. So here's the solar PV. Both of these are from our study. Chris worked huge amount of time, Annalise Alexander also, in calibrating these against very accurate measurements that our laboratory does. We have something called the surface radiation network. So we were able to calibrate, and it turns out all these yellow areas, and especially these red areas, are very rich in resources. And the whole idea is they're kind of complementary. So if you have wind and you have solar and you have big domains, you basically get a complementarity that evens out the available wind and solar energy if you get a big enough domain. And of course that's true not just of the US but also Europe and China. We'll show that. So what did we do? We've worked the last 5 years with our team. We wanted to know the geographic domain size effects of wind and solar generation systems. We basically did a system designer using linear programming that cost minimizes using hourly wind, solar, and electric load for the whole hour at 40,000 grid points over the whole 48 states and 8,760 times per year times 3. So 40,000 by 30,000. So it was a horrendously large computing problem. Thank goodness for our Sheffield graduate, Chris Clack, because he was able to really make the linear programming work. And we actually did a US study which is detailed and a global study which is at lower resolution. So I'd like to now turn it over to Chris to go over exactly what we did. By the way, if you have questions or clarification as we go, please ask. We're going to leave plenty of time for questions at the end and for discussion.
Okay, thank you, Sandy. So what I'm going to go through is the different pieces that we needed to put together to build the system optimization. And then I'm going to pass it back to Sandy to show you two of the main experiments that we did. So first thing we did, which Sandy alluded to, which I'm going to go into a little bit more detail, is collect lots of weather data. And we thought this was the most important part because right from the beginning, as Sandy said, we're trying to build something that integrates large amounts of wind and solar. And if you don't start from that premise, if you build a system, it won't want to accept large amounts of wind and solar. It will be very difficult to then force your way onto the grid. The next thing you need is the electrical load when the weather is happening, because the electrical load, just like a lot of other things, are dictated by the weather. If it's particularly cold, people will put the heating on. If it's particularly hot, they'll put the air conditioning on. If it's dark, they put lights on, and so on. And so then you put these together, and then you realize you have to become a little bit economic-minded, and you have to put it into a simulator. And what we said was, sure, you can build a system where you can put huge amounts of wind and solar on the grid, which makes sure you've got your power. But if you put large amounts of wind and solar on the grid to reliably make power, if you don't do it cheaply, that system will never be built because economics drives everything. So you could build one, and I think there's some scientists in America, Mark Jacobson and others, who have built systems for California, which has a reliability of 99.99%, but the cost is 50 to 60 cents per kilowatt hour for California. And so California went, no thank you, that's too expensive. And so what we're trying to do is we're trying to see is, can you get a high amount of wind and solar working together to make the price reasonable for people to make it palatable to actually invest in this system and actually build the system. The system that we build does include wind, solar, CSP, hydro, nuclear, coal, oil, transmission, high voltage, low voltage, storage, pumped, and electrical. And what we're going to show here is just a couple of those experiments where we simplify things, because the more things you put into a model, the harder it is to fit in a talk in an hour. So we're going to distill it down to just a few of these variables. And then we used it to look at the geographic scaling. So the main thing we want to look at is there an optimal scale that you've got where your benefits outweigh, your disadvantages of having a big scale outweigh the benefits of getting bigger and bigger for the wind and solar. And that's what our main driving thrust is. So back to the weather data. You can tell we're from a weather lab because there's lots of weather. And what this is just a time series of the wind speeds at 80 meters over the US for about a week and a half in 2006. The color bar is meters per second, I think it's 0 to 26 meters per second. And what I want to show here is that the wind comes in off the Pacific, passes through the mountain regions, gets accelerated or funneled in certain parts of the mountain regions, and then flows down the high plains. And so the high plains are, I've got a pointer, in this region here. And where we live in Boulder, Colorado here is about 5,500 feet. And then the Mississippi here is about 0 feet. And between the two is a gradual, steady, flat, well, it's not flat, but smooth grassland downslope. And what happens on downslopes is the wind wants to accelerate down that slope. And so this is why you saw that wind triangle before, because all the wind is washing off the mountain sides. Another thing that I like to show on this plot is that there's always red on this plot. There's always all the colors. In fact, I've been through and been very sad as a mathematician and gone through and checked that all the colors in my color bar are always on these maps at all times. And this is for people that are interested, this is a rastified plot, so there is no contour smoothing. So it's not because I'm contour smoothing. So that's the wind, and that took a lot of effort. And another thing that I want to point out with this is that we did what's called the rotor equivalent speed, which some people don't think is a big deal, but I do. We take winds at different pressure heights throughout the rotor blade, and it gives you an idea of the turbulence and the shear across that rotor blade, and that actually affects the wind output, not only in the amount of power you get, or sorry, the amount of energy you get over a year or multiple years, but also when you get that power. So, for example, during the day, because there's more turbulence and more shear, your power actually drops down a bit. And during the night, where it's nice and stable, your power actually goes up again, which is exactly what you do not want. So you need to take that into account. The next swing is the solar irradiance. So this is just global horizontal irradiance. And the first thing you notice is for half the day, the screen is blank. because the sun goes down. And everyone knows this, but this is why solar has a slight disadvantage, because if you really want to use solar at really high levels, and when I say high levels, I mean over 20-odd%, you have to have some way of storing it, because half the day it's not there. The nice thing about big areas is, though, that there's a 4-hour window between the east and west coast. And what turns out is that the sun is high, or highest, should I say, over the west coast when the east coast is sitting down for supper and putting on their ovens and TVs and watching the USA win their football matches. And so there's a way of correlating the two. And so what we want to do is we want to blend these two together, because they're very helpful for each other. The other benefit of solar for the US, which isn't as true for Europe, is everything in summer is driven by air conditioning demand. And air conditioning demand is very well correlated to how much sun there is. Not entirely surprising, but true. So we found all the weather data. We took a lot of work. I think it's about 3 years of work to make sure that this weather data is right. And so then we needed to get the load data that went with it. And so this is a plot that shows the aggregated US load. So we had to go around and collect all the US loads for all the different regions. And I think there's about 7,000 utilities that you have to go through and go through the government and try and get the information from. And this plot isn't seen very often or accurately plotted. So this is the actual load. And there's 52 notches, which is the weekends. And this is the actual 2007 load. And what you see here is what I explained recently on the last slide. Is this is summer. And so summer is very much dominated by, it gets hotter and hotter during the day, and more people crank on their electricity heat pumps or air conditioning. And then it goes down. But there's superimposed on top of that, there's the seasonal cycle. So we've got the winter, which is got some heating demand. Spring and fall is pretty low, and then summer is this whopping great problem, which is the issue for the US. On the left here is a typical winter week. You see that Sunday is quite low, and it really spikes on Monday because everyone's busy and they're happy to go to work. And then as people stay at home from work, as you get later and later in the week, the load drops off again, and you get the morning rush hour and the evening rush hour as well. And so you get these patterns. So even though this is correlated to the weather, you've also got the social aspect too, which is not dictated by the weather, because Sunday keeps coming around regardless of whether it's raining or sunny. And so we needed that to really work at the problem. And so this is hour by hour data. So then we needed to decide, can we place it wherever we want? And of course, there's a government in the US, and they tell you there's certain places you can't place things: national parks, national forests. Where people live, there's buffer zones around where people live, and it's harder to see. On the left is the wind, on the right is solar, PV, and this is the amount or density that you're allowed to place in the US. So it's in megawatts per kilometer squared or watts per meter squared. It's harder to see on the wind one, but on the solar you'll see there's little boxes that are white, and that's where there's a town more than 42,000 people, and you're not allowed to place it there. On the wind one, I also want to draw attention to offshore wind. This is the maximum amount that could be installed, because we just consider shallow offshore, because deep offshore wasn't price competitive. And there's lots of things that go into this. I won't bore you with them all, but mostly it's slope and population, and then restricted areas to do with the government. So then we tried to do some economics, and we found that was very hard. So we went to other people's papers and refereed journals to find out what they thought the prices would be in 2030. So we used the Energy Information Administration and the World Energy Outlook for most of our study projections. And so we decided to bound our parameter space with 3 prices: a low, and a mid, and a high. And our high are the best estimates that we could find referenceable for today's cost in the US. And then the low is the optimistic price for the US by 2030. As you can see, as the technologies are more mature, that spread gets less and less. So for natural gas, we found that they all really clustered around $1.24, and that's capital and fixed O&M installed watts, price per watt, sorry. Then we have onshore wind, which is again fairly mature, which is quite tight. PV, which is not as tight, and then offshore wind, because in the US there's nothing offshore at the moment, so this is a wildly large spread of data. We then have HVDC lines, and for this, again, we've started simplifying now. We wanted to just test one price, and so we took the average price that we found, including station costs and line costs. And then the big economic lever, if you like, on ours is natural gas fuel cost, because that is the one that is very volatile in the US and can go up and down fairly rapidly. And so we go between $5.40 and $11.10, which is the EIA prediction for 2040. Standard heat rate for the natural gas, and then there's a variable O&M for the fossil fuel generation as well. And so at this point, what I'm saying is we've simplified it to just these 4 technologies for generation. So we want wind, solar, and then we need a backup of some description, which is natural gas. We also do have inside it existing hydro and nuclear generation too. We continue what exists today out to 2030. What's new is the HVDC transmission parameterization. So this is what the network could be built like for the US. So we found the 32 largest electrical load centers across the US, and each of these nodes that we have are of equal land size. Because we're looking at geographic scaling, if we had irregularly sized nodes, then showing a scaling law would be very difficult because you can't divide it properly. So we had 32 equally sized nodes, and they have 32 node centers. And so we need some way of transmitting the power about, and these are the high voltage DC lines. So I'm about to hit you with some math, so I'm going to give you a picture first, because I like pictures first, so that it helps me think about what's going on. So the minimization is really fairly simple economically. It's just the total annual amortized cost of all the installed capacity, plus all the transmission capacity, plus any fuel that's burnt, plus any O&M that's spent. So that's what we're trying to minimize. So every hour, we find out what the generation is, and then we find out how much that's going to cost totally over the year. So we do transmission and generation at the same time. The main constraint to this is obviously that all the generation you're making, plus all the losses that you lose as you transmit this power about, must always keep the lights on. So there's no, in our optimization, there's no downtimes. The optimization has to meet the load at every single hour. For the 128 regions within the 32 nodes. And then every other constraint that you'll see, and I'll show, is specifically designed to constrain what goes on. So you have to have reserve requirements, you have to have ramping constraints and things like that. So that's what I'll go into now. So this, converted into math, is this equation. It's fairly simple, really. You've got the variable generation times by the variable cost, plus the dispatchable generation, plus the fuel cost, so all the fuel you've burnt, and then your transmission costs, which is your station costs plus your line costs. Now these are all amortized costs, so we have a 30-year mortgage term, 6.6% real discount rate. And so this is what we're minimizing through time. And this is the subject too. So this is the more difficult equation. So this is the equation that says our generation in each of our nodes from the variable generation plus the generation from the dispatchable within those nodes must equal the load in that node minus any transmission flux in and out of that node plus any excess generation. And this is for every single hour of that year period. And we do this for the three years separately, and then we look at what the results look like. These B terms here contain the loss function and contain a filter which tells it which node it's in, because you don't want to double count generators. This F term here is actually the difficult term mathematically in terms of controlling a system, because this is a degenerate term, because you have this 3D matrix, which is the actual power flow across this network every hour of the year. So if you build a new transmission line, this whole matrix will change, and then you'll have to recompute everything that's going on in the basis set. So the simple flux term is equal to the flux coming in minus any losses minus the flux that's going out of that network. So you could, in theory, have power flowing into a transshipment node and then all of that power being moved on to another node. To do that, then, you need to have a bound which says my capacity of those lines must be greater than any power that's in that line at any time. So this, again, is done every hour. It says that if I'm shipping 10 gigawatts, my line must be 10 gigawatts. And we put an upper bound on here to constrain it to current technology. So 12 gigawatts is the maximum we can build, because we've been reliably informed that's currently what they can build. They haven't built one that big yet. They've built 8 gigawatts. But if we didn't do that, the optimization would go, oh, that's OK, we'll put in 100 gigawatts of transmission, which will obviously not be built because people will be very unhappy. The next few terms are less important, but they still need to be there. We need reserve requirements for the natural gas backup, so we give it 15%. In each of those nodes, you need to have 15% excess capacity in case there's issues going on within the grid. And again, this has got the filter term. And what we say is at any time step, it must be 15% bigger than you ever use. And I didn't say it earlier, but the wind and solar have a derate factor of 5% for inconsistencies or downtime throughout the whole thing. Last slide of maths. This is the nuclear and hydro ramping constraint. At the moment, we just do this for numerical stability, so it's easier to solve because with the nuclear in the US, you have discontinuities between months because they drop offline to service them. And so here we allow a bit of a smoother ramp so that the merit speeds up. And hydro here, we do the same thing because we actually use the actual output for those years because we didn't model the water cycle because it's a very difficult thing to do. So we just used what actually was output by these generators, and we allowed it a tiny bit of wiggle room so that rounding error doesn't cause an issue. And the last two terms are down to those images that I showed before about you have to have a certain amount allowed in each region. You can't put an infinite amount of wind turbines. Summary slide of what we've got in the optimization. There's 1 million equations, 10 million variables to 100 million variables, and then 100 million to 1 billion non-zeros. And so it took a long time to solve this. And if I take out transmission, this takes 20 minutes to solve. If I put transmission in, it takes about 50 hours. So the difference with the transmission being in there and integrated makes a big difference, but it also makes $50 billion worth of difference in cost as well. So there's a reason it's in there, is because it makes it much cheaper as a system. So two quick studies that we did. The first is the pessimistic view. We get to 2030, natural gas is really cheap, really abundant. Wind and solar is really expensive. Rare metals are difficult to get hold of. This is what the system optimizer builds. So it does build an HVDC transmission system. There is some solar, there is some wind, there is hydroelectric, there is nuclear, but there's a lot of natural gas. Yeah, so the green here is onshore wind. The light blue here is hydroelectric. The reds are solar PV. These there are some blacks, but they're quite difficult to see against the purple, and they are nuclear power plants, and the purples are natural gas. And the grey lines are the transmission lines, and they actually are scaled to the 3 gigawatt thickness here. And because we've taken, yeah, sorry, go on.
Which year did you say this was from?
This is 2007 weather data, but we project the load to 2030. So it's 2007 electrical load grown to 2030 size. And because we've taken out all other things apart from wind, solar, and natural gas and base load, which doesn't include coal, the natural gas takes up a large part of the share. If we were to have coal in here, of course, a large chunk of this natural gas would be coal for this pessimistic case. If we then go to the optimistic case, which is the exact opposite, so we go from this to this, we suddenly see a lot more green appear. We see a lot more red appear, and it's probably can't read it back there, but it's 39% generation from onshore wind, 17% from solar PV, and 21% from natural gas. Offshore wind is 0%, but there is hope. There is one offshore wind farm, 21 megawatts installed off Maine. But what I like to see here is that there is a spread of wind and solar across the whole domain. There is a slight bias towards the east because of losses and cost of transmission to build the pipes across. And obviously, we see that there's a lot of power production in the center. And so the last thing that I shall show is this is the system running. It's a different one from before. This is the 2006 system because I wanted to show a bit more offshore. The system is now running, and when the lines go black, this is power being transferred from A to B, and the colors are rated between 0 and 1, so 0 power to full power in each of those boxes. And what you should see is that as the day goes past, the solar comes online and offline as it rolls across the country, and you can see over on the west coast it comes offline on the east. And so the reason that there's east coast and west coast is the sun isn't up on the west coast when the east coast are waking up, and so they need some solar to power what they're doing. And the last thing that I'll say about this is, at no time throughout any of this is there no wind. The wind is always blowing somewhere on this map, and indeed there's always somewhere where the wind is actually blowing at full power on this map throughout the whole 3-year period. And so I'm going to hand back to Sandy to show you the scaling experiments that we did.
So if you get a big domain, the wind's always blowing somewhere, and this is not a random domain. This is basically a designed domain to meet the constraints that Chris talked about. So what we wanted to do is say, well, that's not what we have now. We have a bunch of little teeny domains. There's effectively about 130 little areas where there's balancing done in the United States. There's other restrictions, like one power company owns this little area and another. So right now it's very fractionated, and the statement that wind and solar don't work is basically, if I want to take my little Georgia Power and Light and for that area put in wind and solar, it's true, it doesn't work. There's not much wind in Georgia, and that little area doesn't work. So we designed an experiment where we basically divided up the domain to see how that would affect things. So the first thing we do is we start with the full domain, and we cut it in half. So you can kind of see this line here where we cut it in half. Then we cut it in to quarters and eighths and sixteenths, and we just keep going down till we reach pretty close to what the US has now. That is, we're optimizing. Chris runs his optimizer for each of these little domains, and I realize you can't see these squares, but I'll tell you the significance. The significance is that as you get to smaller and smaller domains, much larger amounts of gas dispatchable are used. So if you get small domains, it becomes more expensive and generates a whole lot more carbon. These graphs show that. So this is CO2 emissions from the whole system. And down here on the abscissa is the area. So this is the average area of balancing areas in the United States, which is a little less than 10 to the 5th square kilometers. And the amount of CO2, and this is actually, to me, probably a generous assumption, but the amount of CO2 is 32% as much as it was in 2010, mainly because we start with the initial assumption that we're converting everything to gas and there's no coal. But if you take the whole 48 state domain, you get almost cut in half the amount of CO2 down to an 83% reduction. It's only 17% as much as it is in the 2010 mix. And with new rules that essentially allow you to at least probably sequester something like 2/3 of the CO2, that seems like it'll be economically feasible for a reasonable price on the natural gas. You're probably talking about 5 to 10% as much CO2 emissions in this system. In terms of costs, same thing. If you have a 48 state domain, you have that big transmission network. Essentially, the costs are higher, in this case about 13%. There's other cases where it's a steeper curve. And basically, these costs are something like 6 to 7 cents per kilowatt hour wholesale. So essentially, what this says is transmission over a large domain gets you to a point where you can cut over 80% of your CO2 for prices that are similar to the current prices. So we said, well, is this just true for the US, or is it true for other regions? And we did a lower resolution study, but it is less sophisticated, but the results we were able to kind of check against our US results. This beautiful graphic is the winds at 80 meters over the whole globe. We used a global model that we've developed in our laboratory. You can see that the mid-latitudes are pretty windy, but the tropics aren't. Mid-latitudes windy, but not much in the tropics. Not surprisingly, the tropics are pretty darn sunny. So the way we think about this is you can actually solve the mid-latitude wind and solar energy problem by essentially large domains and transmission. It probably is going to take a really good storage and use of solar energy in the tropics. Majority of the world's population does still live in mid-latitudes. So I mentioned that we had done Europe. This is the large transmission-enabled electric system. You notice that it likes to put wind energy along the northern tier. Not quite sure why it decided to put some in Turkey. Maybe it's really windy there, I don't know. This particular one didn't put much solar, and it did put quite a bit of wind in the United Kingdom and Ireland, just again from this global model. If you go to the small domains, in other words, you say, well, you only can exchange electric over small domains. You don't have that big high voltage DC network. Then it tries to dominate each of the small areas with solar, and you get a much larger percentage. That's what this graph shows. And this, in some ways, is probably the most interesting and significant graph of the whole study. We're just about done, so get your questions ready. This is projected to 2030. And once again, we've got area on the bottom. And so this is the area of a US state or a province in China or Germany or the existing balancing areas. And we're using the best estimate of what renewable energy and gas will cost in the 2030s. So our best estimate. So what this essentially says is you're down here below 20%, around 10%. Essentially, wind and solar will not be used if we stay in these small domains. Essentially, if you're going to get large penetration of wind and solar, these ideas that came out a number of years ago, the paper on transmission over all of Europe, and there's been equivalent ideas in the US, it basically says there is a way right now, without a carbon tax, without cap and trade, that using best estimate figures gets us rapidly in the 2030s to an economy that uses far less carbon and without ruining our economies because the costs are about the same. So conclusion, since weather is variable over large geographic scales, wind and solar generation must encompass large geographic areas to be reliable and cost effective. You need the high voltage DC transmission to enable these large areas such as the US, Europe, or China. We didn't go deeply into it, but of course high voltage transmission has a lot less losses, and you don't have the synchronization problem that restricts you to a few hundred miles. In the US study, we found we could reduce carbon dioxide emissions by over 80% with electric costs comparable to today. There's no new technology in this. In the global study, using the best estimate of wind and solar costs, we find that wind and solar energy will not play a significant role in the 2030s because they're being implemented on domains that are too small. So with that, I would like to stop and entertain questions, and maybe I can get you to turn on the lights.
Thank you, Sandy. Absolutely mind-boggling stuff to a mere economist like me. But there we are. Questions, comments? Gentleman at the back and then this one at the front here. Just let us know who you are and where you come from, and then we'll have a discussion.
Hi, thanks for that excellent presentation. I'm a student at Imperial College, and my question is regarding storage. As far as I understand, storage is sometimes seen as in competition with long-distance transmission. Like it's a flexible plant that your storage, you can replace the flexible plant by storage instead of large geographic areas. So my question is, did you look at the sensitivity to the penetration of storage in the electricity system?
Yes, we did look at storage, and at the best price estimates from Energy Information Administration and so on, storage was not competitive. In other words, you don't need storage if, in other words, it doesn't use storage, it's a cost thing, and right now storage is too expensive. Chris?
Yeah, I would like to add that we did do some runs where we made the price competitive to transmission, and it turns out that you still need the transmission because you would need such a large, if you do these small domains, you need such a large amount of the storage that it really becomes a costing again, even if it's cheap enough, because the solar PV is what you're storing basically. The wind sorts itself out over the area. It's cheaper to ship it as just a general thing, no matter how cheap you get the storage. But the PV, you have these big spikes during the day, particularly in the summer, that you need to store, and that's a lot of kilowatt hours that you have to store somewhere, and it becomes very expensive, even with cheap hydroelectric pumped or compressed air. So it's in competition, but it's a relatively minor part that would go into the mix. It's much cheaper to move the power about. So
to reiterate one comment, we've done probably hundreds of runs, and we're showing you just a couple.
Gentleman here. Yes. I understand a lot of work was done on the European supergrid in the 1990s and so on, and there were people like Dr. Sizic, I believe. How do you pronounce his name?
Right, the German.
Yeah, yes, exactly. To what extent is this updating his work and validating it?
You know, we read his paper when we got started with this, and it certainly put us on a road of, well, we have to have HVDC transmission as part of it. In my opinion, his work is foundational. It's very important, and it basically, we come to the same conclusion. In fact, we come to, I'd say, a stronger conclusion, because ours is basically saying, if you build this super grid of HVDC transmission, there's no reason not to start now, and it's not going to cost more than our current system. And I think his was regarded as, well, gosh, is this going to be, you know, this big expensive thing? So money matters.
And on the price of the actual electricity, are you promising us cheap power in the future?
We're promising power that's comparable to today's prices. So we're not, you know, it's complex, because if you, for example, if you take a look at the world market gas price, so there's the European gas price, which now with the Russians shutting off the gas is probably going to go higher. There's the US, where there's a glut of gas. But if you look at 50 years of gas prices, for normal natural gas prices, this system gives you low carbon, low cost power for the foreseeable future. I want to just make a quick comment on nuclear, because I happen to believe that the greatest problem we face is carbon, and I want to mention that nuclear plants or coal with sequestration, as far as I'm concerned, this makes a level economic playing field. If somebody comes up with a really terrific, you know, sort of a little nuclear plant that you can site away from cities because you've got this transmission network, as far as I'm concerned, great. But what this does do is what's so important in economics, that is, it takes where the power plant is out of the equation and says you can get the power anywhere. And unless we recognize that, sorry to go on here, but this is a really important point. In the United States, the creation of transcontinental railroads was done in the 1860s. And in the 1960s, we built our interstate highway system. And this is essentially a superhighway system for electrons that makes essentially huge economic sense.
Can you just give us your name?
I've got to be quick now. I'm just a private individual interested in...
That's all right. That's absolutely fine. You're very welcome. The lady here.
Yes, thank you. Jane Brigginshaw, Homes and Communities Agency. Is this practical, is my question. And you've gone through the economic benefits. So in money terms, I understand the presentation very clear. Socially, is it possible? Could we build these high voltage grids? Could we get the consensus to allow that to happen? Now, I understand that's not your area, but you've certainly thought about it a lot.
As far as I'm concerned, it's my area. So, a lot of people say, well, this would be a huge investment. When I show it to political people, and I've had access to President Obama's energy czar, I've had access to the top levels of the Department of Energy and senior politicians in the U.S. Basically, they see it, it looks to them like a 48-state jobs program. In other words, build infrastructure that is going to make us more economically effective, sort of take being beholden to the Middle East and places where oil are now out of the equation. You know, you don't have to go fight wars if your energy is internal. So they like it in that sense. There's another part of your question, which is, oh my gosh, we're going to have these big ugly power lines. The lawyers will never let us do it. You know, there are answers there too. I'll give you a couple, and you know, every country is different and so on. But one answer in the United States is that in the 19th century, when they built the railroads, they gave the railroads so-called land grants. The railroads in these laws written in the 19th century have every right to put a power line up from one end of the railroad to the other. So they can build overhead power lines already, and the railroads are really looking at this closely. Now there's a different answer, and I think it's an important answer, because that is what's going to happen with underground power. So right now, if you take a hard look, and to me, money is everything. If you take a look at what ABB, for example, and other companies are looking at for what it costs you to put power underground, it's probably a factor of 2 away from overground. It's not a factor of 10, and they're looking at how they get more and more sort of capacity and therefore less cost. So there are answers already to the question of could we build it.
Just a very quick question. I seem to remember that Gregor Chish looked at using pumped hydro or existing hydro in pumped mode to smooth the electricity supply from his predominantly wind system. But you...
We don't. No, and we don't for the, I'm going to call on Chris here in a second, but we don't for the reason everything is like it is, which is it doesn't compete economically. In other words, everything in this is, the most important thing is price. If people can get power for the same price, okay. So what's the story in that?
So for the European one, it's basically a very simple model. So we only looked at 3 resources: wind, solar, and natural gas. So hydroelectric doesn't play a part in that one.
It's not hydroelectric though. He's talking about pump storage.
Pump storage,
right?
Because it didn't compete. So we tried it. It didn't compete. So we took it out so that we could run them again faster to make sure that the results were the same. For the US, they're in there, and there is pumped hydro in there. And when we did experiments with the pumped hydro in there, it was about 100% of the load was used through pumped hydro, because it's very limited to where you can place them, because there's lots of hydroelectric dams that you can't do it in pump mode. And so it just wasn't used because it's not a viable way of doing it. So for the US at least, where we looked at it in detail, it's very difficult to turn some of those into pumped hydro.
A crucial point is there's nothing I'd like more than to see a breakthrough in some kind of energy storage, because essentially it would make these results that much stronger. But cost-wise right now, it didn't compete over the US.
Can I just ask a question again on these costs? You've obviously factored in the cost of the HVDC, so that's in there, and you're talking about mid-range costs, so you're being not too optimistic but not too pessimistic as to what your projections are in 2030. But you've also got natural gas costs in there, and as we know, natural gas prices in the US recently have fallen through the floor. What kinds of natural gas prices are you assuming for 2030? Are you assuming that the shale gas revolution peters out a bit and that gas rises in price again, or are you keeping the natural gas prices at their very low level today?
We don't keep them at the low level. One thing we did is we took the 50-year inflation-adjusted price of natural gas, and it's got a cycle. It goes way up and way down. And you know, as somebody who started my career working for a gas driller, I understand why that happens, because the price of gas goes up, all the gas drillers head out and they start buying capital equipment and they start doing it, and about 5 years later the price of gas is down here and they all quit. And actually that's where they are now. We've actually, even with the shale gas on the Bakken Formation, which is where I was raised, the shale gas price is down. So if you look at it over a long period of time, so we basically used estimates that are the best Department of Energy estimates, which we thought were reasonable. We're kind of at a low point for gas cost, but the fact that, you know, we have these difficulties with gas in other parts of the world, that the U.S. is going to try and get a big export market going, we think the figures we used are pretty good.
Thank you very much. Gentlemen here, do say who you are.
Daniel Skidmore from Foster & Partners, Architects Engineers. I'd just like to echo my neighbour's comments here, because in this country the amount of stress and hassle trying to get one railway line built or a third runway at an airport is deep enough. So I think the socio-political issues are probably much more vast than many of the other kind of technical issues that we're worrying about, because often those can be solved. I think whether we can convince governments to work together in that way is always the really tough part on any of these kind of.
Yeah, let me sort of be the third member of that club. So we've written a paper which we're going to submit, you know, to Nature or some other journal. And essentially what I say in there is that the legal, commercial, social, and other impediments really sort of almost dictate that we stay at these small scales. And that's why I start with that diagram that says, okay, but if we stay at those small scales, we're going to have the equivalent of an Eocene equilibrium climate in, you know, not long, 2050. So it's true, it's very hard to do. And then when I talk to ABB and some other companies, and they say, yeah, we can put it underground. I haven't done this yet, but this is the way it works, you know. I'm sort of working away in my management job, and then I walk down the hall to Chris and I say, Chris, why don't you try this out with the actual ABB cost for underground transmission? Because in the United States, Congress in one day could essentially say, we're going to put underground transmission right away along all the interstate highway systems, and you pretty much have that network. So I haven't walked down and told him that yet, but if it's underground on existing public right-of-way, voila, you sort of cut through the Gordian knot of all that.
I mean, America's, I'm not going to say it's an easier climate to work in, because in some ways a lot of power companies are even more fractured than what it's like even in the UK or what have you, but it's really complex. Maybe China's the only one that...
Well, you know, I've even heard that. I've had people say, well, you know, our democracies have evolved so much since the Magna Carta that our systems are so complex and we can't deal with changes no matter how great the incentive. And of course, I'm kind of an optimist. I believe that there are solutions like put it underground along existing right-of-way, And I don't think actually England or UK is any more complicated than the US. I spent 7 years, most of my last 7 years in Washington working as a senior official, and it's complicated, but the incentive is huge.
Yes, gentlemen there, and then we'll come over to you.
Thanks. Mark Jane, I'm Senior Research Fellow at Oxford University, and also a technical representative of the International Energy Agency (BPS) program, photovoltaic power systems program. My question is related to your, obviously, did most of your modeling and analysis based on economic cost. I wonder, they usually go hand in hand somewhat, but not necessarily always. So I wonder if there's any sort of parallel analysis also in terms of energy return on energy investment. So taking the economics out of the equation, just looking at how much energy investment in terms of primary energy in is required per unit of energy output.
Yeah, so that's a good point. The way that I usually think about that is when people have brought this point up, and by the way, I've given this talk, 40 or 50 times. When people bring that up, I say, okay, what are we going to charge as an externality for the cost of releasing carbon into the atmosphere? So if you'll allow me to set what is a reasonable cost for, say, a carbon tax for releasing, then I could do the analysis that you're talking about. If you don't do that, coal in the United States is 3 or 4 cents. If you build a new coal plant and you don't worry about it, is 3 cents. So that's cheaper than this system. So that's the real question associated with that. What is the cost of releasing CO2? And a lot of people say, well, nothing for me right now.
Yes, I'm Godfrey Boyle from the Open University. Thank you for a very convincing portrayal of how the spreading over a large scale can reduce the need for storage. Can I bring you back to the storage issue for a moment? In that the conventional wisdom of storage seems to be just too expensive. A lot of work's been being done in Germany with what they call power to gas. You probably have seen the audience, I'm sure you know that. Converting, first of all,
right.
carbon dioxide,
Right.
using the spatial process to convert it into synthetic methane, and then power into the conventional power grid. But I deduce from your knowledge that you've looked at this and found that it's too expensive, but maybe you can tell me what you think about that.
Well, no, I think it's, I think it's sort of at an early stage of development. Part of what we're saying is, well, we expect PV costs to come down, and we expect wind turbine costs to come down a little bit. And that idea that the Germans are working on, which is basically you put it right next to a fossil fuel plant like a natural gas plant, and since you've got sort of this high density of CO2, you can create the methane. I say that for Chris's honor, because whenever he says methane, I say, no, it's methane, So, but that's to me a really worthy thing to find out, because all of these ideas like that, if we could make inexpensive storage, that would be terrific. You want to add to that?
It takes advantage of the existing
infrastructure. It does, yeah. Yeah. So you're really basically able to use the methane as your storage. Anything you want to add?
Yeah, we did some experiments on that where we just played around with the price. So we used Tandem to produce it. We ran into some difficulties as well. How long a time period do you need to store up in your transmission system? The natural gas transmission system in the US isn't quite as easy to ship the natural gas about. So there's very strong localized markets. But we looked at that and we found that you can remove pretty much all the natural gas for about 10–15% more if the price of the stability air process is down to the equivalent of what wind costs, so $2 or $3 per watt. If you can get it to there, then yes. But what we try to do with these studies that we're trying to present and publish is today's technology. So you can build it today, and then if you my sort of optimistic side is that you would do this process and then you can get rid of that last 20% by converting to much more extravagant, more things that are coming faster online, and then of course convert more things to electric heating, water heating, for that. So.
Yeah, so that sort of gets us from 17% CO2 to 0% if we can do that, and we're definitely interested in that.
I'm going to take just 2 more questions because we've really reached the end of our time. I think I've seen a gentleman at the back, and then there's one at the front. So just like to say who you are, and then let's take them both at the same time, and then you can divvy them up between you as you feel you like.
Sure. My name is Jonathan Gaventa from E3G, which is a think tank based here in London. My question is that there's been a couple of studies looking at the European system and the potential grid systems and looking at the sources of value, most notably by the European Climate Foundation and colleagues at Imperial College London. And one of the things that really struck me from that is similar numbers about it being more economic, but it was suggesting that only part of the value comes from putting the renewables where it's windiest or sunniest or whatever, and much more of the value comes from actually using your conventional power plant for backup and balancing in a much more efficient way, basically running the plants first and making best use of the system. Did you find sort of similar outcomes in your analysis, or is it mostly driven by really accessing where the wind is and where the solar is?
Let's take that question. It's quite a detailed one, so.
Yeah, essentially, I didn't really get into it, but the existing U.S. natural gas generating capacity stays about the same in this system that has essentially, about 60% wind and solar. So essentially what that says is it is using sort of existing kind of installed capacity, but I don't think I quite got your question. Do you have a better beat on it?
So one of the ways that we deliberately made it more conservative is that each region had to have a reserve requirement. So when you get to geographic scaling, the benefit you get from diversifying your portfolio is that you don't need to have the reserves locally. What we did deliberately was we said, no, you still need to have those reserves locally. So most of the benefit you're getting here is actually by getting the resource where it's best. There obviously is some benefit because you can then transmit that power using the HVDC that has been built, but the majority of your benefit is coming from load diversification and the resource being in the best place and being correlated with the load. And but there would be more of an effect if we, rather than saying we had to have 15% reserve in every single region, you could say we need 15% for the whole fleet. Then you would have a bigger, steeper curve. But we've done that experiment, but again, we kept trying to keep everything as simple as possible.
And the final question.
Okay, John Silmarsh from the Department of Energy and Climate Change. It's very much just a supply-based model, and I was wondering whether you'd looked at the sensitivity to the reduction in demand. You've got sort of a great deal of energy efficiency going on. Does that make any difference?
Well, there's a couple of points. One of them is in David McKay's book, he makes a wonderful point, which is it isn't just the electric sector you care about. You really need to deal with the light-duty vehicles, and you need to deal with space heating and air conditioning. And so if you take all three, essentially we had some interesting sort of looks at what does it take to do all three, and he converts everything into kilowatt hours per person per day. And so a quick calculation was if we could get the US, which is one of the most profligate use of power, to just sort of do reasonable reductions of their electric power use. I think Chris did a calculation that showed that you could almost cover your whole light-duty vehicle fleet from that power saving. So I guess I think that the problem that we face is we have to do like McKay has in his book. You got to convert all three sectors. So I've said, well, this is going to be a growth of the electric sector, but it would be a so we didn't look at a decrease. You want to add to that?
Yeah, so we did look at, like we said multiple times, lots of other scenarios. So the main one that we looked at was, I was talking about this big sort of, not discontinuity, but difference between winter and summer. There's this big sort of hump in summer which you need to overcome, and the weather doesn't suddenly give you some miraculous energy source in summer. And so we looked at heating water with heat pump water heaters and heating and cooling houses with air conditioning heat pump type scenarios, so we can bring up the wintertime load, which is when your wind in the US particularly is blowing the hardest. And you can then pull down slightly your summertime load. So the load actually grew in terms of energy, but you were equalizing the load. And it actually makes the system because you don't have this 400 gigawatt difference between summer, it's more like 200 gigawatts. So we didn't look at decreasing because I think that, personally, so it might not be true, but I think things will go to electric because they'll be easier to deal with, and then because that's where these technologies are going, and so that will actually grow, which is why we've explicitly done electricity rather than the whole energy system, because I think we can convert to electric, which will be easier to go to, because if the subsea air process, even though it's great, you're going from the lowest energy back to the highest energy and then burning again, so you're going back up and down, a very inefficient process, whereas if you can keep it all electrical, it's easier to deal with. I don't know if that was it.
So yeah, so sort of a future that really does deal with, you know, the great problems of CO2 in the atmosphere and being dependent on oil imports and gas imports from unstable places, and sending people like Chris to Afghanistan to protect our sources. That's sort of the future that says, let's go all electric. You know, you're going to be able to drive your Tesla cheaper than paying for the gasoline. So that's the future we looked at.
Okay, well, thank you very much indeed, Sandy and Chris. Huge pleasure to hear such good science coming out of the US. Of course, we know there's lots of good science in the US, but even a bigger pleasure to know that there's such good sense on energy and climate change being taken to the heart of Washington at high levels, because we don't always get that perception over in Europe. So thank you very much for making it quite clear that in fact those messages are getting out there and presumably are being heard, and at some point hopefully there'll be a US administration that says we can do it. Let's fight that bullet. Very much.